crux of the research paper, attention is all you need. Welcome to One Research Secret. Before we get into the details of the video, let me show you a cheat sheet of the research paper with all the details in visually rich format. You can get your copy using the link in the description below. This is the second video on transformers. In the last video, we covered the prerequisites of the paper by explaining attention mechanism. In this video, let's have a walkthrough of the paper. Discussing introduction. We already had state-of-the-art approaches like RNNs, LSTMs, and GRUs, which were used for sequence modeling and transduction problems. The main disadvantage is that these models are sequential in nature and they process sentences word by word. Hence, they require a high computation time. This paper's solution is to use transformers. It doesn't employ recursion but uses attention, thus allowing for parallel and faster computation. Let's discuss the model architecture. The transformer model consists of few components. We will discuss each one of these one by one. Its two main components are encoder and decoder stacks. A layer in the encoder and decoder is mainly made up of normalized multi-head attention and feed-forward layers. 6 such layers are stacked. Let's look at the multi-head attention in more detail. We already have discussed attention mechanism in our previous video. This picture illustrates dot product attention with K, V, and Q as input, that is, keys, values, and query as input. The type of attention used in this paper is the multi-head scaled dot product attention. Different combinations of the keys, values, and queries of the same input sentence are projected, and the scale dot product attention function is applied. It is applied on parallel on all these input combinations. Each of these parallel layers are called heads, which is then concatenated to get the final values. That explains the encoder decoder blocks and the operations within it. Say the transformers model is used in language translation task. In the training phase, the English sentences are given to the encoder and the French sentences are given to the decoder. Given the English words and the previous French words, the decoder predicts the next French word. How does it do this? Let's take a look at it layer by layer. We all know that neural networks work only on numbers. So we need to represent words as numbers. For this, we use word vectors, which represents words in such a way that similar meaning words are similar in numerical representation. This happens in the embedding layer. Since the words are fed into the model in parallel and not word by word, we have the positional encoding layers. These layers add token positions to include information of the position of the words in the sentence. We have similar meaning words together and the order of their occurrence too. But how do we know which word is important in a sentence? For that, we use attention mechanism. A weight or score for each word is calculated, which determines how important the word is. Attention mechanism is applied in the encoder and decoder. This is to the input French sentence, input English sentence and the provided output French sentence. The entire French sentence is not given. Only the words before the French word to be predicted are given. This technique is done using masked multi-head attention layer in the decoder block. So with the help of the English and French vectors, a feed-forward network inside the decoder produces a vector. The softmax and the linear layer help in converting the decoder's output vector to probability scores. The word with the highest probability is the output of the model. This is the predicted French word. We now understand the working of the transformers model. Now let's take a look at the few facts. Here we have what was used to train the model. It was the WMT 2014 English German and English French dataset. The hardware setup was 8 NVIDIA GPUs. Base models were trained for 12 hours, big models were trained for 3.5 days. For English to German, it achieved a new state of the art score, blue score of 28.4. For English to French translation, it achieved a score of 41, but at less than half quarter the training cost. Adam Optimizer was used for optimization along with dropouts and label smoothing for regularization. In this paper, the base model was varied, measuring the change in performance on the development set. Here in this table, I give you the variation that was done on the model and what observation was made as an effect of it. Alright, congratulations! You have understood the intuition and the explanation for the super important transformers model. In the paper, they stated that future plan is to apply them to the other tasks that handle large inputs and outputs such as images, audio, and video. Now we see that happen in DALI and other models. And now it's quiz time. In my last video, I had a quiz, which was what are the inputs to the attention function? Keys and values, keys and query, values and query, keys, values, and query. Leave your answers in the comment section below and let's see how many of you get it right. The correct answer is keys, values, and query. Now to the quiz of this video. In multi-head attention, the output of the parallel attention layers is A. Averaged, B. Concatenated, C. Multiplied, or D. Subtracted. Let's see if you can answer them right in the comment section. Since it's difficult to understand research papers, we simplify them for you in this channel. If you liked what you learned so far, like, comment, and subscribe. If you would like to get a copy of the cheat sheet and answers to the quiz, click the link on the screen or in the description below. Thank you.